Okay, everybody, we're going to do a fairly short video on exponential growth and decay. And I just want you to have a basic understanding of what's going on. This is real world applications of the exponential equation stuff that we've been studying. So basically, these are the ways that mathematicians, scientists, people like that will model exponential growth. So I mentioned before, I think when we were doing compound interest and stuff, when we did the A equals PE to the RT, the continuous compounding and stuff like that, and the population growth. So that's one of the places where people really like to be able to model stuff and see what the heck's going on. So what you'll see is some of this, I'm just going to give you two basic graphs. This one is a basic look at what exponential growth will look like. And hopefully when you hear growth, you think, well, that's getting bigger, right? Growing is going up normally. So what happens is you will have some initial starting point, okay? And usually speaking, as long as we haven't shifted anything or done anything weird, there will be a starting point that is basically, normally this is t for time, right, is what's going on here. And going up, we'll have our function, whatever that is, and we'll see different ones. But this starting point is like your y-intercept. It's where t equals 0, so where did we start? And we're going to have some variables for that. They're going to call it a sub 0 or a naught, and that's just an initial amount. A stands for amount, just like it does in the compound interest formula. But the 0 down there, it's a little subscript, and it means initial starting point, basically. And with growth, we see things are getting bigger, okay? And when you hear the word decay, hopefully you think, decay usually is going to mean something is getting smaller, right? So think about a plant that has been broken off and it doesn't have nutrients or water anymore. It's just laying on the ground. Eventually it will decay, okay? So a lot of times people call that a half-life and want to know what's going on. In that case, we'll have still an initial starting point where t equals 0, time equals 0. From the beginning, this is how big it was, or this is how much nutrients were in there, or whatever. But then it'll shoot downward, right? Okay. So these kind of look like the exponential functions we've had. The thing is, usually our exponential functions, we have a tail on them, and we're not going to have this tail over here in the negatives because time isn't negative, right? Time starts at 0 for us and moves forward in minutes or seconds or whatever we're measuring, okay? There are two basic formulas for these that we're going to see. One is, well, sometimes they give it to us as a function, okay, where we take the a sub naught, or that's the initial amount, and we multiply it by e to the kt, okay? And I'll explain these in a second. So that's if you're looking at it as a function, or they may say a. So remember from our compound interest formulas, a is normally amount. So initial amount times e to the kt will give me the amount at the end, okay, is the way we read that. So depending on which one you're doing, okay, the a sub naughts are the same. This means initial amount. Okay. If we use this second version, then this is the ending amount. The A is the ending amount, okay? That's still what f of x or y stands for if we had that as a regular equation instead of function notation. But they're going to be an amount. That's the end of the thing. So what else is going on here? I have the variable t, okay? So t is time, and it just depends on the problem that we're working on. That's the same t, stands for time. And the e here is the natural number, e, 2.718, blah, 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 blah. We would round it to 2.72, or you'll use your button in the calculator, right? So that e is not a variable, remember, okay? E is a number. is approximately 2.72. It is not a variable. You're not solving for it, okay? And then this K is the weirdo. We've probably not seen a K before, right? So that's the variable we're like, oh, that's totally different. In this case, K stands for the growth rate. Okay. So rate of growth, some people actually even put an R in there, although R normally stands for interest rate. So that's why in these models, they give it a separate letter K. Okay, so it's the growth rate. Now think about it. In this one over here, though, whenever oh, sorry, you can't see the thing. Here, when I've got K, this is K is positive, right? So K is greater than 0. Positive, but here where this guy's coming down, that's decay or decrease. K is going to be less than 0, right? Those are negatives in my exponents is what that ends up being. So this might be a positive 3.9 T for growth. And this one over here might be a negative 3.9 T for the decay, okay? The difference being that when the K is greater than 0, I increase. And when the K is less than 0, I decrease. That's the difference, okay? So either one uses the same formula though. Notice I can use that formula for either one, growth or decay. And what's gonna make it grow or decay is whether or not my K is positive or negative, okay? Can your K be 0? This is a question I have for you. No growth rate is what that means. It's not growing, it's not decaying, it's just standing even. Well, if this is a 0, then T times 0 would be 0. And we know anything to the 0 is a 1, right? So E to the 0 would be 1. So basically, if you don't have a growth rate at all, you're left over with the A sub 0, right? So if there's no growth and there's no decay, K equals 0, then you're just always going to be left with your initial value. So that's how you're going to read these formulas, all right? Either this one or this one. It doesn't matter. All right. So let's see how this works. Here's an example. How people, and in particular, you end up seeing scientists use these formulas a lot. So how are they utilizing these? How are they applying things? So the problem says we're going to model the growth of the U.S. population. The graph in figure 4.22 shows the U.S. population in millions for 5 selected years from 1970 through 2010. Okay, so, and it's if you wanted to see it in the book, it's a bar graph basically, right? So those are the population numbers, okay? We don't really care about that because in the problem, sorry about that, in the problem it tells me, it says, in 1970, the U.S. population was 203.3 million. Okay, that's a lot of people. But in 2010, the U.S. population was, sorry, 308.7 million. Okay. So really quickly, is this growing or is it decaying? We started here in the 70s. We ended up here in the 2010s. It's a growth, right? So this is a positive K. So we have a growth model that we're going to be looking at. So that's not part of the question. It's just I'm asking us to think, what are we looking at? So if we were to graph those numbers that they gave us in the bar chart, we'd see something that looked something like that. I don't know exactly what it looks like, but that's the basics of the graph. Okay. So the question says, find an exponential growth function that models the data for 1970 through 2010. So we got to start there, looking at the growth model so far. So we don't know a ton. We're going to figure it out as we go along. We need to start with the basic growth model. So I'm going to do the A equals A sub naught e to the kt. And I'm specifically picking this one because I do know the amount at the end of time, right? At least by 2010, I know that amount. So I'm going to have my A as well, let's start over. The A sub naught is going to be my initial value, right? This is my start. Or my A sub naught is the way we work. And this 308.7, that's going to be my end at the end of, well, 40 years in here, right? Okay, so that's going to be my A. So let's make sure everybody gets that this is a 40 years difference. Okay. So when I look at that, I've got, okay, my starting value was in 1970. I've got my ending value in 2010. The E is a variable. I don't know K. That's what I'm looking for. I want the growth rate first, and then I'll get the model that goes with it. Okay. But I do know the T equals 40, right? So let's do some plugging in. All right. My initial value was 203.3. Oops, I need a thing, 203.3. E to the, I don't know what the K is, but the T is 40 for 40 years. And that equals my ending value, the A is 308.7. All right, there we go. All right, now what? Well, I need to find K, right? This is going to give me the growth rate. And once I get that growth rate, the question actually said, find an exponential growth function that models this. So that's what we're after. But first I have to find that K so I can stick it in to the growth function. So here we go. I've got this guy. Let me clean him up just a tiny bit. 308.7 equals 203.3 e to the, I'm going to make that a 40K. Okay. And I see, hey, I've got this exponential function and the K is in the exponent, and like normal, I don't want the K in the exponent. I want to bring it down, and we know I can do that, but I can't do it whenever the E is being multiplied by something. Here's the exponential part. Does everybody agree? E to the 40K, that's the exponential part, but it's multiplied by this 203.3. So before I can do anything else, I've got to get rid of that 203.3. How do I do it? And in my head, I hear you saying, well, these are multiplied. So to get rid of this, I need to divide. So divide by 203.3. And what I do to the left, I have to do to the right, or what I do to the right in this case, I have to do to the left. And so these guys will go away. And on the right-hand side, I'm just going to have e to the 40K, right? That's what I'm after. That's what I want to see. Astute. Okay, but on the left-hand side, I need to find out what that number is. It's 308.7 divided by 203.3. So I've got 1.518, and it's a big long decimal. I'll be sure to keep that in my calculator so I don't have too many rounding errors. But for right now, I'm just going to write 1.518, and we'll deal with it in a second. All right, now look. E to the something equals something. I can totally move this guy around. If you want a log base answer equals exponent, the idea is get the K out of the exponent, right? Now that I've got the E all by itself, the exponential part of this by itself, I just need to get the K out of there. So if you want to do log base answer equals exponent, you can. Just be aware I've got a base E. So when I log base it, that's going to be ln for natural log, right? Okay. Or if you prefer, you can take the ln of both sides. I don't care which way you do it. I'm probably just going to ln both sides, because I know that whenever I do that, remember, we've got this exponent up here. We've got that power rule that says for my logarithm properties, I can pull that down in front, right? So this becomes ln of 1.518 equals 40K ln of E, because when I'm raising an exponent to an exponent, I can pull this down and multiply them. We know that. And then there's a log rule that says whenever you have a log with a base here, as that's the same as here, that those is just a 1, right? So basically, remember, this guy is saying log base E of E. Well, that is a 1. Okay, so this is a 1. Okay, so that guy's just going to kind of go away because it's multiplied by the 40K and we don't care. So what I've got is ln of this 1.518 guy. Now I've got that in my calculator. So what I'm going to do, I'm going to find my ln button. Remember, it's right here beside your 4 button. ln, and I want that last answer. So I'm going to second and the negative sign down here. It's next to the enter button. And it'll bring up answer. So ln of whatever your, ln of whatever your latest answer was. And so that is, again, another big long decimal, 0.41, I'm going to say 8 is a bunch of junk, equals 40K. And we are almost done. We just need to simplify a little bit. Remember, we're looking for K. So to get K completely by itself, hopefully you're thinking, well, it's multiplied by 40. What do we do? Get rid of multiplication? We divide. So we're going to divide by 40. That'll give me just a K on the right-hand side. But remember, whatever I do on the right-hand side, I have to do to the left-hand side. So I'm going to divide this guy by 40 also. I'm going to move this around so I have K equals, just so I can find my growth rate. I've got this long decimal. I'm going to divide it by 40. And I've got another long decimal, so my K is basically 0.0104. 0.104. And it doesn't look like that's going to round. I'm going to leave it like that for 4 decimals. Sometimes they'll tell you how many you need, and sometimes they don't. Okay, so I'm not done yet with the question they asked me. They said, find an exponential growth function. Exponential growth function that represents the data, basically. Okay, I've got my growth rate. So let's find this again. Okay, it was A equals A sub 0, my initial value, e to the kt. So let's see it. This is the form I want to put it in. A equals A sub naught, e to the kt. Okay, and they want me to give this as a growth function. Okay, now when I do that, what I'm going to see is we're going to have the output will be the ending value. So that's going to be a variable when I'm finished. And the t is going to be a variable because I don't know how much time is passing on each one. So those are going to stay the way they are. The things I should have values for is the a sub naught, or my initial value, and the K, which I just found, right? Remember, E is not a variable, it's a number. So A equals, remind me what my A sub naught was. The initial value in 1970 was 203.3. So 203.3. E is just along for the ride. He's not a variable, he's just a number sitting there. The K I have, it's right here, e to the 0.0104, and t is going to stay a variable. Okay, so what this tells me, there's my formula, my growth function. Okay, what this tells me is, okay, if you put in t equals 12 years, okay, I'll get out the population value then. If I put in t equals 40 years, I better get out the population in 2010, which we know was 308.7. So this guy, I put in whatever time I'm at, I'll get out the new population. Okay, there's our function. That's part A. Part B says, by which year will have the U.S. population at 335 million. Okay, so let's think about that, 335 million. Remember, this was 2010, the population was 308.7, okay? They want to know in which year will the population be 335 million? Well, so that's the case where I'm trying to plug into the A, because the A is the amount of the population. And I want to know which year that's the T, right? Okay. So let's do that one. I'm sorry. 335 equals 203.3 e to the 0.0104. That's the same number, t. So the idea here is I'm going to use the function we just came up with, and I am going to solve for t. It's going to tell me how many years, and then I can figure out where that is from the initial. Okay. Well, you know, this looks an awful lot like what we just did. Instead of solving for k, though, I'm going to solve for t. So it's the same process of what we just did. So I'm going to divide by 203.3. And if you want to do this by yourself and see if you can solve for t all by yourself and push pause, and then I'll come back, that's great. I'm going to divide and get the number over here. I'm going to keep that number in my calculator. This is going to become 1.648-ish. Okay. And then I look at this and I go, oh, hey, that's e is by itself. I'm going to take the logarithm of both sides. I'm going to do ln because it's an e. And because I did that, I'm going to be able to pull this exponent down in front. I'm going to kind of combine a couple of steps here. Sorry. So that's the ln of 1.648 is equal to 0.0104 t times ln of e. But we know ln of e is a 1. So that's going to go away. Because when I multiply 1 by this thing, I just get this thing. And then I'm going to be able to punch that on my calculator. So I've got this 1.64 guy. And like I did before, I'm going to ln and get the answer. So the ln of that answer is 0.499. I'm going to put it right here because I'm out of space. Sorry. 0.499 equals 0.0104 t. And just like before, I got to get the t by itself. Earlier it was the k, but same process. Divide. So hopefully if you did this all on your own, you were able to work through the process, and now you can unstop me and see if we got the same answer. So 48. It's about 48.023 is the t. So that's not quite the answer, but we're getting there. It basically tells me that the population is going to be at this point in about 38 years. Okay. I'm sorry, 48 years. Let me get the right number there. So how do I come about 48 years? What that is? Well, that's 48 years after 1970, right? Let's see what that is. I don't know. 48 equals 2018. So supposedly we reached that population, 335 million people around 2018. Now the thing is this, these are models. They're not diehard predictions. It's possible that it doesn't get to be exactly what we think it's going to be. And we just do the best we can in order to get to an answer and hope that it models. And most models are really good in the short term, but not so great in the long term. So if you look through things, all of these problems work exactly the same, so I don't want to work a ton of them. It's just that if your K is a negative, you get decay instead of growth. That happens sometimes whenever they try to carbon date stuff. Like if they're trying to figure out how old a dinosaur fossil is or something like that, they take a little scraping or whatever, they figure out how much carbon's in it. They use a carbon dating process, which is basically exponential decay formula. And that's how it tells them how old they think it is. But again, remember that these models are almost always really good in the short term, but may not be as accurate as we get farther out. So if we're talking like tons and tons of like over 40 years, they're probably good. 48 years, we're probably pretty good. But if we're talking thousands of years, sometimes things get a little messy. All right. So there's also a thing out there. There's lots of different kinds of growth models. This is the one that most closely relates to what we did in class with the exponential functions. But there's other kinds of growth models out there. And if you went on into, say, an advanced statistics class, you might have to do some kind of logarithmic growth or logistical growth or something like that. So just be aware there are other kinds of modeling out there. This is just the one that we are going to use. And occasionally, I mean, like this one has the E at the base of it, but occasionally they may actually have their own E for the base that they're working off of. So that's about it. That tells us all about exponential growth and decay. And I'm going to stop this video because that's long enough. I hope it makes sense. If you have questions, let me know. Thanks.